All right, so let us continue on. Section 3.2 is on the definition of the derivative function. So up to now I've just been talking about finding the derivative of a function at a point, but we want to recognize now the fact that since you can do that at each point in the domain of many functions, that allows you to define a new function using the derivative at each point, the so-called derivative of the function, right? And so the new function, which denoted f prime, is called the derivative of f. It's defined pointwise by f prime of x equals the limit as h goes to 0, f of x plus h minus f of x over h. Excuse me. We can also use the notation f prime df dx or df dx like that. If u is a subset of the reals, when the function has derivative f prime which is continuous on u, we say that f is in C1u. That means it's once continuously differentiable. And if the derivative has a continuous derivative f prime prime on u, we say f is in C2u. Alright, that would be twice continuously differentiable. And if we can take arbitrarily many derivatives which are continuous on u, then we say it's a smooth function. We denote this by f as an element of C infinity u. Alright. Now, excuse me. Here we go. Example. Let's find the formula for the derivative function for the square root. So f prime of x, limit h goes to 0, f of x plus h minus f of x divided by h. Alright. Now, what we're looking at here is the square root of x plus h minus the square root of x divided by h. Now, that's type 0 over 0, right? But the way to deal with ones like this is to multiply by the same thing, but with a plus. So, let's see here. I will multiply by square root of x plus h plus the square root of x divided by square root of x plus h plus the square root of x, like so. And so what happens, of course, is these, it gives you like square root of x plus h squared, right? And then minus the square root of x squared. The cross terms cancel, right? Alright, and then what happens? Square that out. My handwriting. So horrible. So the x's cancel, then the h's reduce, and you're just left with the limit as h goes to 0 of minus 1. Oh no, there's no minus 1, excuse me. It's the x's cancel, then the h reduces. There's no minus 1 there. Plus 1 rather, over the square root. X plus h plus the square root of x. Whew. So that is 1 over square root of x plus 0 plus the square root of x, right? Which we can simplify as saying the following: d dx. Alright. Of the square root of x is equal to 1 over 2 times the square root of x. This is one of our laws of differentiation, actually. So it's the kind of thing you actually would like to memorize. But of course, if I ask you to show that this is true from the definition, then you need to work it from the definition, yeah. But it's also something that it would be good if you had memorized. Let's see here. Next up, I have 1 over x squared. Calculate the derivative from the definition. So, pretty straightforward, right? F of x plus h minus f of x. So that's 1 over x plus h. Wait a minute. Why? Oh. Well, there's a typo here. See this? That's wrong. This was f of x equals 1 over x. That's the example that's being done. See, because it's f of x is 1 over x. So you put x plus h, you get 1 over x plus h minus f of x minus 1 over x. So that was a typo. Alright, so there we go. I make a common denominator here. Then the x's cancel. Then the h's reduce. Then you can plug in h equal to 0. You get minus 1 over x squared. And so what we get is that df dx is minus 1 over x squared, or this right here, the derivative of 1 over x is minus 1 over x squared. Cool. Now, so far, we're doing everything from the limit, right? And so I actually use the derivative we just found to sketch some tangent lines to the 1 over x function, either side of the vertical asymptote at 0. Move along here before I start coughing like a madman again. Alright, so linearity of the derivative in the power rule. So on your test 1, the majority of test 1 is on limits, right? And just like the basic notation stuff we went over, you know, intervals and number line, that kind of stuff, you know. But mostly limits, all right? And also definition of the derivative at a point. But I do have a little bit of space reserved on test 1 for testing you on the basic rules of differentiation, because it's so important. I want to make sure I test it twice. So that's what section 3.3 is on here. These are the fundamental rules of differentiation. And here they are. First of all, if you've got a constant, you can pull it outside the derivative. Alright? Second of all, if you've got a derivative of a sum, the sum of the derivatives. So these two things collectively I call the linearity. These two collectively I call these linearity. Linearity of the derivative operator, d dx. Excuse me. Now the proof is pretty straightforward from the definition of the limit, limit-based definition of the derivative. So if I have f and g that are both differentiable, and I look at f plus g, and I look at that difference quotient, and I just expand and group things, I get a difference quotient in f and a difference quotient in g, and that's f prime of x and g prime of x. And similarly, for the pulling a constant out, you can sort through that the difference quotient for a constant times a function is the constant times the difference quotient for the same function. So there's that.
Daddy, I need some paper.
You need some paper. You're not supposed to be in here, though.
I need this kind of paper.
Oh, you need that kind of paper. You must be making me a book again.
I just need this many I need.
Okay, this many you need. Oh. You shouldn't be in your mat, buddy. Oh. Whew. They have been told to stay away from sick daddy. Oh, but they do not listen. Alright. So next up, we have a laundry list of important basic derivatives. First of all, the derivative of a constant. We already saw this was 0 for 3. It's the same calculation if you do it for f of x equal to c. Anyway, the difference quotient works out to 0. So the derivative of a constant is 0. d dx of c is 0. Alright. Where was I? The function f of x equals to x, this is sometimes called the identity function, because it just, like f of x equals to x, it's like, it's the identity, right? But anyway, if you calculate the derivative of that, you get x plus h minus x over h. X's cancel, and the h's reduce, it gives you 1. So there we go, d dx of x equals to 1, or if you like, dx equal to 1. So it does kind of help you along the line of wanting you to think that dx is just a tiny little thing and dx over dx is actually a fraction. But anyway, I will not chase that rabbit any further. The derivative of a quadratic function, f of x equals x squared. So x plus h squared minus x squared over h is the difference quotient here. Expanding x plus h squared, we get x squared plus 2xh plus h squared minus x squared. Of course, the x squared and the x squareds cancel. Now leaves us with 2x plus h squared over h, which simplifies to 2x plus h. As h goes to 0, that just gives us 2x. So the derivative with respect to x of x squared is 2x. And next, the cubic function. Oh no, I see a typo here. Oh, goodness gracious, folks. Look at this, f of x equals to x cubed. Come on, man. Come on. Alright, anyway. So f prime of x, x plus h cubed minus x cubed, right? That's the difference quotient for the cube function. Expanding out the cube gives you these 4 terms. The x cubes cancel. They leave you these 3 terms. The terms with h's go to 0 on the limit, and it just leaves you 3x squared. So we have that d dx of x cubed is 3x squared. So in a better world where I hadn't got COVID, we would have had a lecture where I did this in person, and we would have had an aha moment where we started noticing that there was a pattern here. But we're being forced to do it through this video, so here we go. So examples that we have done: ddx of 1 is 0, ddx of x is x, ddx of x squared is 2x. And you can start to notice that there's a pattern here. And the pattern is that ddx of x to the power n is n x to the n minus 1. This is the so-called power rule. So, like here, n equals to 2. So you have 2 times x to the 2 minus 1, which is x. Here, this one power rule is also right. N equals 3, so we have 3x to the 3 minus 1, which is 2. Power rule. All right. Sorry. So this is the power rule, as I was just saying. So I give a proof here, which is based on that binomial theorem we talked about, remember? With Pascal's triangle and all that. So this is where I needed that calculation that I was mumbling about. It only really matters the fact that there's an n and then the next leading term. This is where that happens. So like x plus h to the n, it's x to the n plus n, x to the n minus 1 h, plus everything here has got a power of h squared or higher. So essentially when you take x to the h plus n minus x to the n, first of all you're gonna cancel out the x to the n term. And second of all, everything that's got h squared or higher, it's going to limit to 0, because after it divides out the h, there's still at least one h left, which limits to 0. So the only thing that survives this limit is this term right here, n x to the n minus 1 times h. And so that's essentially the proof of the power rule by the binomial theorem. Yep. Now, this of course assumes that n is an integer, and we've already seen examples where the power rule worked even though it was an integer. For example, the square root function is n equals 1/2, and you had 1/2 x to the minus 1/2. So it's actually the power rule. But so the power rule worked, and that wouldn't be covered by this proof, right? So we'll give another proof later that covers the fact that in fact the power rule is true for n in the reals. I've only given a proof for n in the natural numbers right here. All right. So let's look at this in-class example. My main goal here is to get through these in-class examples with you guys. Using the power rule correctly mostly boils down to you having good grasp of law of exponents. Very true. ddx of x times x to the 4th. So we should do ddx of x to the power 5, which would then be 5 x to the power 5 minus 1. That's the power rule. In other words, 5 x to the 4th. There you go. Hooray. In-class example. Next. Here we are. Here we are. Alright. You can use linearity in conjunction with the power rule for added fun. Yay. d dx, d dx. Alright, so we're looking here at 3x squared plus the square root of 4 times the square root of x. See, because property of the square root. Now, and x cubed over x is x squared, yeah. So what I got is I can pull the 3 out of d dx of my x squared, and then square root of 4 is 2, and then I have to do d dx of the square root of x. Alright, now we just worked that out like a few minutes ago, but this is 3 times 2x plus 2 times 1 over 2 times the square root of x. Remember I said we should memorize that? Well, there you go. Cool. I said sometimes the independent variable is not x, rather t, or even t or what? Ah, stupid printer. I can't see anything. Or even mu. ddt of ttt, ddt of t cubed, 3t squared, okay. ddc of c is 1, dd mu of mu to the k is k mu to the k minus 1. Sure, I'll buy that for $1. Why not? Why not? Alright, here we go. Extended linearity. If you have more than two things added together and constants multiplying them, same song and dance, you can pull the constants out, you can break across the sum just like you like. The proof is by induction. I leave it as a exercise to the elusive creature, the curious reader. Something my advisor used to say. Anyway, where are we? In class example 3.37. d dx of x plus x squared plus 3. Alright. So, I'll try to write out my work. d dx of x, d dx of x squared, d dx of 3. So d dx of x is 1, d dx of x squared is 2x, d dx of 3 is 0. So it's 1 plus 2x. If a, b, c are real numbers, calculate this derivative. If you don't mind, I'm just going to do it without the steps. Well, fine, I'll do the steps. Oh. A d dx of x squared, b over 3 d dx of x cubed minus d dx 1 over x plus d dx of constant cubed. So the constant cubed is still a constant, so that's just 0. And so what we got here is 2ax from that term, that's 2x. This gives us 3x squared. The 3 cancels the third, so we get plus bx squared. The derivative of 1 over x was minus 1 over x squared, but there's a minus here already, so it's just plus 1 over x squared. So there you go. Reminder, you can check your work in Wolfram Alpha on this stuff, right? You're not alone. Of course, Audric in the Tutorial Center can help you. This stuff is like, you know, super easy for him. Alright, so here's another example. Question. What is the slope of the line y equals mx plus b at the point x naught, mx naught plus b? So the question is d dx of mx plus b, right? That is going to give me of course we get m. The slope of the line at that point is m, which is not terribly surprising, but anyway. The difference now, guys, is like I didn't have to do a limit, right? I could use the laws of differentiation to do it this time, right? And I don't know about you, but like using the power rule and linearity, it's much nicer than using limits. So when I allow you that freedom on the test, take advantage of it. And make sure you know how to do these. They're not that hard once you get started. Oh, goodness gracious. Whew. Another hill to climb here. What is the slope of f of x equals to ax squared plus bx plus c at the point x naught, f naught? What is the significance of the point where f prime of x naught is 0? Alright. So if f of x equals to ax squared plus bx plus c, then f prime of x is d dx of ax squared ddx bx ddx, of course, of c, which is going to give me 2ax plus b. Alright, so hence f prime of x naught is 2a x naught plus b. Alright, well, there you go. Very exciting. Answered that question. Right? And what's the significance of the point where f prime of x naught is 0? So you can think about it. F prime of x naught, 2a x naught plus b equal to 0 tells me that x naught equals to minus b over 2a. Aha! This is the x-coordinate of the vertex of the parabola. Which makes sense, right? That's going to be the place where you have, slope. You have a slope 0. Yeah. Yep. So yeah, the significance is if we set the derivative equal to 0, we're going to find turning points in the graph. And generically speaking, those are places where we could have a minimum or maximum in the function looking forward. Now this particular one, though, I recognize from classical geometry and previous coursework and such that, well, that's the formula for the x-coordinate of the vertex of the parabola. Oh, goodness gracious. Alright, moving along. F of x equals 3x to the 7th plus 2x squared plus 5. Find the equation to the tangent line at 1. Great. So f prime of x is equal to d dx. 3x to the 7th plus 2x squared plus 5. So that works out to 21x to the 6th plus 4x. Derivative of 5 is 0. So f prime of 1 is 21 times 1 to the 6th power plus 4 times 1, which is 21. 21 plus 4, which is 25. So the slope is 25. And the equation of the tangent line is, let's see here, what's f of 1? I always forget to check that. Well, it's 3 plus 2 plus 5. It's 10. So 10 plus 25 times x minus 1. There you go. Equation to the tangent line. No limit. Just use the linearity power rule. Easy peasy. Much easier. Even a very sick instructor can do it. Alright. Could you see it? Was it in the film? Yeah, it was in the film. Alright. Oh, hooray. We've reached near the end. Okay, so the exponential function. We talked about the exponential function before, and essentially the issue is how do you define e, and so e is probably, well, I mean, not probably, e is named e in honor of Euler, and so here's how to calculate the derivative of a to the x in a somewhat sneaky way. So a to the x plus h minus a to the x. So I use laws of exponents. Factor out a to the x. I got a to the h minus 1 over h. So then a to the x is just a constant. I pull it out. So whatever this limit is, that times a to the x is the derivative of a to the x. So it stands to reason there must be a particularly nice choice of a, which makes this limit be 1, and you can define that real number to be e. Well, that's the approach I take in these notes. So, at least for now. And so that is why, since this limit is 1, and this calculation up here, it follows that d dx of e to the x is e to the x. So, particularly easy derivative right there. Now,
I don't know what scribble is, but I put tape on this.
you put tape on that.
And here too.
Hmm.
And show a picture about the Empire robot.
An Empire robot?
The Empire.
Oh, okay, yeah.
That's what that.
Oh, that Empire robot.
That was it called.
Oh, an Empire robot. Good guy or bad guy?
Bad guy.
Okay.
And this, so if robot Sheen can make souls come out of it, so it can do that. And this is assuming men or assuming something like that Facebook like that.
Uh-huh.
And this called machine can make things look like a shotgun going Iron Man shotgun.
Buddy, you better go. God.
Look about a picture.
Benjamin, better go, buddy. I don't want to cough while you're here.
I'm closing the door.
Oh, okay. So, anyway, the exponential is its own derivative. And the exponential is a very interesting function. There are at least 5, well, I think I have 4 different, seemingly different ways to define it here. And so I'll let you look at that if you want. When we get to Calculus 2, we get this power series definition, which I'm particularly fond of. But any event, I hope this helps. I'm sorry it's been so kind of pathetic. This is all I've got to work with at the moment. Phew, I don't know if I'm going to make it through that Zoom tomorrow. We'll try though.